All right. Good morning, grade 12s, and welcome to Thursday. Um, Unfortunately, I am not in again today. However, I will be in to school tomorrow. Okay. Yeah, it's been a busy week. Newborn baby keeping us busy around here. But I will be in tomorrow for sure. So I will see you all tomorrow. I will have your tests marked from before the break. So those will all be back and handed back to you. Um, and we will chat tomorrow about the plan for this test. Okay. Um, Either we're going to be doing it on Monday or on Tuesday. My thinking is, well, I have two thoughts. If we do it on Monday, it allows for back to back 2 full days of review for the culminating activity, okay, which I think would be beneficial. If we do it on Tuesday, that does still allow us to have that'll allow us Friday and Monday to do 2 full review periods. Those 2 review periods could be used for whatever you want. If you wanted to review for this unit test, or if you wanted to work on course review, you could do either of those on those 2 review days. So we'll chat on Monday, or sorry, we'll chat tomorrow about when the test is going to be. As long as, hopefully you've been completing the homework, hopefully you've been following along with these videos, and if you've been doing that, this unit, you know what, you should be prepared to do the test on Monday. However, I do understand that with me being away so much this week that you probably do have some questions, and those questions I'll try to answer tomorrow as best I can. And based on how you're feeling, we can make a decision tomorrow on whether we'll do the test on Monday or on Tuesday. Okay? So we will chat about that tomorrow. So please be in class tomorrow, and I will answer as many questions as you all have. Okay. This is our last lesson for the course. Okay. Our last lesson for the course is today. The rest of the days of this course are review periods and culminating activities and our test day. Okay. So that's the plan. We're going to go through our final note here today, and it's basically going to look at solving different problems involving rates of change, involving instantaneous rates of change and average rates of change. And so what we're going to do, I'm going to go through this lesson. There are 5 examples in this lesson. There's a few homework questions posted at the end. The homework questions are scattered throughout. I'll just scroll down. They're kind of scattered a little bit throughout a couple different chapters there. You notice 103, 111, 235, 369. We've chose some questions that are from various units because this topic here can be done in a number, or is covered in a number of different units. Okay. So let's get started. All right. So today, like I said, we're solving problems involving rates of change. Okay. So it says here, very first to start, it says that a rate of change is a measure of how quickly one quantity changes with respect to another quantity. Okay. Very easy example to think about here is when we think of a rate of change, we can think of kilometers per hour. How fast, right? The idea is how quickly are my kilometers changing with respect to hours, right? If I'm going 100 kilometers an hour, that means that every hour I'm going 100 kilometers. Every 2 hours I'm going 200 kilometers. Okay, that's what rate of change is how quickly one thing is changing with respect to another. The average rate of change, which we looked at on Monday, represents the rate of change over a specific interval. Okay, so just quickly here for this one, right? If we look at average rate of change, we're looking at, if I draw a graph here, we're looking at the rate of change over a specific interval. So maybe from here to here, and we're looking for the slope between that. What is the average rate of change between those 2 points? Okay, notice that it changes. So we have to draw a line and figure out the average rate of change between 2 points. Instantaneous rate of change, on the other hand, is when we look at a specific point. Instantaneous rate of change, we're looking at what is the slope or the rate of change at one specific point on a curve. Okay. So those are kind of things, three kind of things that we looked at earlier this week. Now, let's take a look at some displacement time graphs, or we could call like distance time graphs. Okay, because that's kind of a big topic that we look at here, that we'll look at in these word problems that we'll answer. So it says here that when the rate of change of displacement or speed, right? Displacement time is speed, is constant. Okay, constant means it's not changing. The slope is the same. An increasing line indicates that displacement increases as time increases. So as time increases, you could think of this as maybe my displacement from home. As time increases, I'm getting further and further and further away from my home. A decreasing line, just give me one moment. So the next one says a decreasing line, okay, decreasing line indicates that displacement decreases as time increases. So in this one, if I, as time increases, I'm getting closer and closer and closer to home. Imagine that's displacement from home, okay? And my rate is constant. My rate of change is constant. Okay. The next one. When rate of change of displacement or speed is variable, meaning it's changing, it's not constant, is variable, an increasing curve, okay? Notice how these curves are both increasing. As I go from right to left, they are going up. As I go from right to left, they are going up. They both have positive slopes. So it means my displacement is increasing. Okay? Both of these graphs, although they look slightly different, are both the displacement. You're going further and further away from home. Okay? You're getting further and further away from the x-axis. In the first one, however, the speed is increasing as time increases. You can tell that because the graph is getting steeper. Getting steeper. In our second one, the speed is decreasing as time increases because this one is getting less steep over time. So we're slowing down. Okay? For this one here, a horizontal line indicates that there is no change in displacement, which means I'm not going anywhere. So there's no speed. Okay, my speed is 0. My rate of change is 0. Okay. And for my last one, notice with both of these, as I go from left to right, I'm going down, 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 down. So I'm decreasing. As I go from left to right, I'm going down, 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 down. So I'm decreasing. So the speed here in the first one, though, is I'm starting off going quickly towards the x-axis, and then I'm starting to slow down. So in this one, my speed is decreasing. It's leveling off. I'm going closer, and my curve is getting flatter, means it's getting closer to a speed of 0. In this one, my displacement is going down. I'm getting closer to home, or it could be a negative displacement, a negative rate of change, a negative speed. But my speed is in this one. My speed is negative, but increasing as time increases. And we tell that because as I go from left to right, my graph is getting more and more steep. Okay? So that's kind of the difference here. These first two up here, this one and this one, we're getting further away from home. In the first one, we're getting further from home faster and faster and faster. In the second one, we're getting further away from home slower and slower and slower. In this one, in number 3, we're getting closer to home, but at a slower and slower and slower speed. And in this one, in the fourth one, we're getting closer to home at a much faster and faster and faster speed. Okay, we should probably slow down quickly in the fourth one, or else we're going to run right through the house. Okay, hopefully those make sense there. Okay, again, please don't hesitate to check this video out again for more clarification. Okay, and like I said, I will answer hopefully as many questions as I possibly can tomorrow. And wear my running shoes. All right. This one says, Sarah, let me just make sure I'm recording. Okay. Sarah is walking to work. So what we're going to do for this one is we're going to draw out a distance time graph. And then we're going to draw out a speed time graph. Okay, so we're going to look at what does her distance time graph look like, and how does that compare to her speed time graph? Okay, so Sarah is walking to work. So I'm going to read this once, and then I'm going to read it again and draw. As she started walking, she sped up. Well, this should say sped up for 2 minutes. Then she walked at a constant speed for another 3. When she realized that she would be early for work, she slowed down. She came to a complete stop once she reached work 10 minutes after she started. Okay, well, I'm going to start with one piece of information here. The first piece of information I'm going to start with is that it said she reached work 10 minutes after she started. Okay, now she's walking to work. She starts walking, and it says that she speeds up for 2 minutes. Okay, so for my first 2, I'm going to go 2, 4, 6, 8, 10. So my first 2 minutes, she's speeding up. So she's going slow, and then faster and faster and faster and faster. Okay, notice how my graph is getting steeper and steeper and steeper and steeper. Okay, so that's my first 2 minutes. I'm just going to draw a little dotted line there to show that first 2 minutes. Then it says, then she walked at a constant speed for another 3 minutes. So now her speed is constant. Okay, how do we show constant? Well, we show constant by drawing a straight constant line, constant slope. Okay, not curve. And that's for another 3 minutes. So that would give us till about 5 minutes. And then it says, when she realized that she would be at work early, she began to slow down. Okay, she came to a complete stop once she reached work. Okay, so what she's going to do, she came to a complete stop once she reached work. So she's going to continue at this constant speed, and then what she's going to do is she's going to start to slow down. So that all that means is our graph is going to get less and less and less and less steep to the point that it becomes flat at the 10-minute mark. She reaches work after a total of 10 minutes, so our graph should be flat at 10 after 10 minutes. So now she's at work for the rest of the day. Okay? That's what that graph looks like. Okay? She sped up for the first 2 minutes. She walked at a constant rate for the next 3. And then over the next 5 minutes, she slowed down until she came to a complete stop at work. Now, how does that look in terms of our speed? Okay? Well, in terms of our speed, for the first 2 minutes, okay, 2 and then to 5 and then to 10. Those are kind of our key blocks here. So for the first 2 minutes, she's speeding up. Her speed is increasing. Okay, her speed is increasing. Now, we're going to say her speed is increasing. We don't know at what rate her speed is increasing, but her speed is increasing. So we're going to just draw that as a straight constant line. Her speed is increasing. Now, at from 2 to 5, her speed is constant. So her speed is not changing. Okay, so that's a constant line. Her speed is not changing. And in the final 5 minutes, she's slowing down as she gets to work. So her speed is decreasing until she comes to a speed of 0. Okay, so that's a time speed graph, which kind of just focuses on her speed. Okay, is her speed is increasing, her speed is constant or 0, or sorry, stays the same, and then her speed decreases back to 0. Okay, we'll draw those lines just as linear because we don't. It's tough to kind of decipher visually just by looking at the distance time if she's increasing her speed at a constant rate or not. Okay. All right. We're going to scroll down here and get into some more examples. A couple things here. The tangent line. So remember, a tangent line touches one point on a graph. The tangent lines at a maximum point or minimum point will always be horizontal lines. Okay, so what does that mean? Well, if I draw a graph here, and let's draw a sketch of a quartic function. Okay, with this quartic function, at the maximum, let's pick a different color. At the maximum points, maximum, minimum, maximum points, if I were to draw my tangent lines in these places, my tangent lines are going to be horizontal lines. Okay, those lines are horizontal. What that means is that the instantaneous rate of change is 0 at these points. Okay, so that's important to note. The slope or the rate of change at the maximum and minimum points is O. Oh. I don't know what that was. I'm sorry. I just I gotta pause this. All right, my apologies. So you're getting the uncut version here. I'm not going to edit that out, but I do apologize for the term that I use there, using the Lord's name in vain. I do apologize for that. I guess I'm a little on edge. Something fell in our front hallway, and it spooked me. So I'm a little jumpy. I'm typically a little jumpy, and so you got a little. I got a good scare there. My heart rate is coming down though, and I think that I am ready to continue. Okay. Whew. This next point here says a minimum will occur if the instantaneous rate of change is negative before the value where the rate of change is 0 and positive after this value. Okay. And all that means is it's a minimum. Let's look at our minimum here. Okay. This minimum point here. If we were to look at the rate of change before and then after, right? Notice that before it's a negative slope and after it's a positive slope. That's all that's saying. Okay. If we look at a maximum, the instantaneous rate of change of a point before would be positive, and the instantaneous rate of change of a point after would be negative. That's one way that we can determine or tell if a point is a maximum or a minimum. Okay? Okay, so example number 2. It says, show that the minimum value for the function f at x equals x squared minus 4x happens when x equals 2. It says use the difference quotient. So remembering from yesterday that our difference quotient dq is f of a minus h, plus h. Let's fix that. F of a plus h minus f of a all over h. Okay. Now we use this is our a value. So we're going to sub that in. We're going to say f of a plus, I'm rattled. F of 2 plus h minus f of 2 all over h. And now what we're going to do is we're going to plug in our formula. So this is going to become, our formula is x squared. So I'm going to do big brackets. I'll do big brackets like this. So we're going to go 2 plus h squared minus 4, 2 plus h. So I sub in 2 plus h into my formula. And then I sub 2 into my formula. Minus 2 squared minus 4 bracket 2 all over h. We're going to simplify this. Okay. This becomes, so simplifying this bracket here, what you want to do, and I want you to make sure, because I had students were making this mistake earlier in the year. Remember to do here, this is going to be 2 plus h times 2 plus h. You need to FOIL that, okay? When you FOIL and simplify that, you get 4 plus 4h plus h squared, okay? Minus, I'm now going to distribute this into my bracket. So that's the highlighted part. I'm now going to distribute that 4 into my bracket. So that's minus 8 minus 4h. So that's my whole first bracket completed. And then this is going to be minus 2 squared is 4. And 4 minus 8 is negative 4. Okay, this is all over h. Now I'm going to simplify. So I'll group my like terms. These two here make a plus, right? So this becomes 4 plus 4 minus 8 plus 4h minus 4h plus h squared all over h equals, these things cancel out, these things cancel out, and all we're left with is h squared over h, which is just h. And remember that dq, or our difference quotient, is basically our slope of secant. Okay? And remember, for h, what we're focused on here is we want when h is really, really small or close to 0. So if h is really, really close to 0, what is our slope of the secant? Okay, well, this, as it gets closer and closer to 0, it's going to be, our slope of the secant is equal to 0. So therefore, m secant is basically equal to 0. Okay, so therefore, we've proven that it is, this proves that it is a max or min. So we've proved that it's a max or min. Now we need to show how do we know that it's a minimum, okay? And in order to show that it's a minimum, so this was step 1. In order to show that it's a minimum, we need to determine the points on the left and the right. Okay, so let's do this. All I'm going to do here is I'm going to figure out, okay, what is f of 2, right? What is f of 2? I also want to know what is f of, pick a point to the left of it, 1.9. And what is f of, pick a point to the right of it, 2.1. Okay. And what you're going to see here is this is going to tell me some information. Okay, so if I sub in 2 into my equation, I get, so let's sub in 2. So I get 2 squared minus 4 times 2, which is negative 4. If I sub in 1.9, 1.9 squared minus 4 bracket 1.9. If I sub that in, I get negative 3.99. And if I sub in 2.1, 2.1 squared minus 4 times 2.1 is equal to negative 3.99. So what that looks like on a graph is these 3 points. Let's plot these 3 points. So 2, here's 2, and it's negative 4, which would be roughly here. And so 2.1, let's say this is 2.1. So this is 2, and this is 1.9, right? 1.9, so this is 4. So these 2 points here are negative 3.99, right? So this graph is going to look like this. Okay, so this is a minimum. All right, so subbing in points. So you could determine the slopes to the left and to the right, but it's actually, in this case, just easier to look at, just figure out what the y values are to the left and to the right. Okay, I'm just going to check what my time is here. Okay. Again, I was hoping I could do this in one video this time, but unfortunately not. I have 3 examples left to do here. So what I'm going to do right now is I'm going to stop mark part 1 here, and I'm going to start part 2 of the video. Okay? So we'll see you all on part 2.